So here in 4.2, we're going to talk about the mean value theorem, or commonly known as MVT. Now, this is a mean value theorem. This is not a mean value theorem. It's not unkind, but the mean there refers to mean value, and we'll see how that comes in later. Okay, so the goal here is actually to guarantee the existence of points with certain derivative values. If you remember, we had the intermediate value theorem, IVT, earlier, where we guaranteed that the function would take certain values. That was the function we were talking about. So we guaranteed, with the IVT, we guaranteed the function would take certain values. Now we're going to try and guarantee that the derivative will take certain values. All right. So we're going to start with a simplified version of mean value theorem first, which is Rolle's theorem. So let's look at Rolle's theorem. Rolle's theorem, it does have some requirements. So let f be continuous on the closed interval AB and differentiable on the open. We're going to be repeating that over and over again. And this is going to hold true for mean value theorem too. Continuous on the closed, differentiable on the open. All right. Rolle's theorem also requires that f of a equals f of b. So if you're going from a to b, you need to have the same values of the function at a and b. We'll see that in the graph. All right. So if you have those three things, then there is at least one number c in AB such that f prime of c is 0. So somewhere on that interval, you'll get a place where the derivative is 0. All right. Now that may be hard to understand at first, but you're going to see that this is actually quite reasonable. All right, so let's take a look at this graph here. So here we have points A and B, and their values, f of a and f of b, which are at the same level. So f of a equals f of b. So what we're trying to say is, under the given conditions, that somewhere the derivative has to be 0. So derivative of 0 would show up on a graph as a horizontal tangent line. So basically, if I thought that this theorem wasn't true, then I would need to be able to get from the point at A to the point at B without creating a place for the horizontal tangent line. Now notice that, let's say I start from A and I head upwards. All right. Well, if I'm going to get back to B, I'm going to have to head down again. All right. And from there, I could go straight to B, or maybe I come down, I go below, and I come back. All right. Now doing this, what you see is I've actually created two places where I have a horizontal tangent line. Right there and right there. So those are two places where the derivative is 0. So in fact, I have a C1 and a C2 where I've gotten a 0 derivative. So that, remember, the theorem says there is at least one number C in AB such that f prime is 0. So as you can see, we can get more than one. All right. So let's make note. F needs to be continuous and differentiable, though. We'll see in a minute why that has to be true. An interesting thing here. The theorem doesn't tell us what C is. It doesn't give us the value of C. It doesn't even prescribe a way of finding the value of C. Although, with our examples, the ones that we're going to look at, we're going to be able to do that just to verify the truth of the theorem. So the theorem doesn't tell us what C is, just that it exists. So this is common in mathematics. This is known as an existence theorem, and the IVT was the same way. It just tells us that there is a point where something is happening, but doesn't tell us how to get it. It doesn't even guarantee that we would be able to get it, just that it's there. All right, so let's take a look at a couple of other graphs and see what might be going on here. So in this first graph here, we see that we do indeed have f of a equals to f of b, great, but f is not continuous on closed AB. All right, we've obviously got this discontinuity here, hence the theorem can't say anything. All right, as it turns out, there isn't any place where the derivative is 0, but there could have been. It's just the theorem doesn't apply, so I would say Rolle's theorem does not apply. Can't make any guarantees. All right, here, again, we have f of a equal to f of b. F is continuous on closed AB, but if we look at that point there, we see that f is not differentiable on open AB. All right, so again, Rolle's theorem does not apply. So that's where we are. We can't make any guarantee. It could have worked, but the theorem doesn't guarantee that it will work. It can't. All right, here's one where we have f of a equals f of b. We have f continuous on closed AB, good. And we have actually f is differentiable on open AB, good. Okay, so Rolle's theorem applies. So I should be able to find at least one place where the derivative is 0. And in fact, I see it looks like there's a place there, there's a place there, and there's a place there. So I have one C there, I have another C there, and I have another C there. So there are 3 places in this particular one where the derivative is 0. We were guaranteed at least 1 because all the conditions held, but we actually got 3.